When you go to Wikipedia and look up Newton's method, you'll find the general definition of the root finding method that uses tangent lines. I have an entire video on this topic. It also notes the method can be extended to complex functions and systems of equations, and I have videos on these. In fact, if you Google Newton's method nonlinear system, my lesson will be above the fold. Lastly, it also notes Hausdorff's method and Halley's method, using tangent hyperbolas to approximate a solution. I have videos for both of these topics as well. The trouble comes that when you look up Halley's method on Wikipedia and on YouTube, there's no explanation for how to use it to solve a nonlinear system until now. Hello Internet, this is Oscar Release. In this lesson, I'll be going over generalized Halley's method to solve nonlinear systems. I'll provide an overview in history, then show an example, and finally give some discussion. I recommend that you have some familiarity with generalized Newton's method as well as Halley's method for finding roots. Recall that with normal Newton's method, we need f and f prime, but Halley's method needs f, f prime, and f double prime. But what does something mean to be a derivative? If we think of a more physical example using physics, you might have a position function. Its rate of change is velocity, and velocity's rate of change is acceleration. The same is true of our functions. When it comes to a system of equations, the rate of change of the system is the Jacobian, and then taking further derivatives gives you the Hessian. These partial derivatives give you an understanding of what those functions are doing, although it's kind of hard to visualize. Let's look at this paper by Annie Coit and Paul van der Kruisen. And fun fact, it was actually communicated by J.F. Traub. The authors give this generalized version of Halley's method using this formula, although it's not exactly as simple as that. They use a math that is very similar to Taylor series, giving this expression for x star. A is this function. They write, first we observe that the Newton iteration is the result of its first two terms, meaning if you replaced A, you would get Newton's method. With three terms, we get this form, which was derived by Ehrman in a different manner as an improvement of the Newton iteration, referring to this paper by Hans Ehrman. Another way to approximate x star is to use the 1-1 ARA, which gives this form, which is a generalization of a formula of frame and a rediscovery of the Halley correction, now for systems of equations. When referring to Frame's paper, they mean this one. Let's look at an example. We'll use the same system from my earlier videos. Here we'll need our system f, our derivative Jacobian f prime, and our double derivative f double prime, also known as the Hessian, which in this case is actually a constant. These are the iterations from our system. Notice that it converges very quickly. In this example, we didn't exactly save a lot of iterations by using the more complicated Halley's method. How much faster is Halley? Regarding the order, our authors write, among other new methods, an interesting third-order procedure is constructed via inverse interpolation with n equal to 1 and m equal to 1, essentially Halley's method. This method is preferred to the method of tangent hyperbolas, which is also of third order, since it requires less numerical calculations. But hold on, wasn't Halley's method also the method of tangent hyperbolas? What's going on here? They cite iterative solution of nonlinear equations in several variables by Ortega and Reinbold. They write, several authors have considered extensions to n dimensions. Such a typical process is the method of tangent hyperbolas, which may be formulated as, I'll show you in the next slide, and can be shown to exhibit cubic convergence. On the left, we have generalized Halley's method, and on the right is a generalized method of tangent hyperbolas. There are two versions of that method, but they're both the same. Note that both use an A term, which includes f prime, and with generalized Halley's method, we take the inverse of f prime as well, so that saves us on something, but generalized method of tangent hyperbolas requires another inverse afterwards. Continuing the quote from earlier, however, methods of this type, which require second and higher order derivatives, are rather cumbersome from the computational viewpoint. Indeed, much recent research has been devoted to finding methods needing fewer derivative computations than Newton's method. As a parting thought, Halley's method can be used to solve systems of nonlinear equations with a cubic order convergence, although it does require having another derivative. It also differs from the method of tangent hyperbolas, being more efficient, and I couldn't find much relating to a generalized version of Householder. One probably does exist, but as far as I know, it's an open question. Still though, just use Boyden's method, it's a lot more efficient, and I have a video on that. The code that I wrote was posted on GitHub. As always, thank you for watching. Links to all the sources I used for this video will be located in the description box. I have a few more videos coming on nonlinear systems, so definitely subscribe so you don't miss them. And again, thank you for watching.